Hello, everyone. It's my pleasure to introduce today's speaker, Lucas. Lucas is a global change ecologist interested in using quantitative methods, including simulation modeling and landscape ecology tools. While he's from Brazil and spent many years doing research in remote areas in the Amazon, since 2011, he has been working here in Hawaii. Here he has focused on developing research projects and related decision support tools that directly inform conservation management on the ground. In fact, he is most happy when he can make life a little easier for those doing the hard work of conservation on the ground. In the last few years, his life has been entirely engulfed in a project to help plan for the recovery of over 400 at-risk species across Maui, Nui, which he will talk about today. Thank you so much for being here, and we look forward to your talk.
Is this microphone?
Don't count on it as a bird. It actually receives the sound of a bat.
Okay. Okay. That's good. Okay, hello everybody. Thanks so much for having me here today. Thanks NREM, thanks Melissa and Jada for organizing.
We're seeing your video.
Oh.
Here's what it looks like on.
Oh, okay. Right. Let's see. Let's fix this. Let's do the monitor there. So, that's does that?
It's still there.
Oh, I know what it is. We're sharing the Zoom is sharing the different. So that's.
I know it was working perfectly right before we started. We must drop by.
Yeah, so that's fine. That's fine. Okay, let's go. Good. There you go. Okay, this will work. Pretty confident.
Yes.
Okay, good. Okay, great. All right, as I was saying, thanks everybody for being here today. Thanks for NREM and Melissa and Jada for helping organize this. Okay. And most importantly, I want to thank everybody that's been involved in this big, huge project that I have been involved in the last few years. It's everybody from field crews, the manager, the planners that have been engaged in this big, huge spatial planning exercise. It's my spatial prioritization team, Chad, Christina, and Devin, and so many other people that have made this research possible. Do you know, is everybody online can hear and everything?
Yes.
Okay, good. Good. So anyway, so today I'm talking to you about this large conservation planning exercise that I have been helping along for the last 3 or 4+ years. And this is something that we were approached by Scott Fretz, who's the head of Maui Nui DOFA. And he had a really big problem that he wanted to find a solution for, which was he is the person responsible for managing over 400 at-risk species across Hawaii. And they span plants, invertebrates, all, forest birds, seabirds, water birds, so forth. And he just needed a better and coordinated approach to do this kind of work, to prioritize where to do this work across a very vast landscape, covering multiple islands, and multiple different sets of species. And he just needed a better, more concrete plan to help him prioritize all of his efforts, his limited resources, coming up with a plan that would help him essentially do more with less, and especially with the emphasis of trying to better co-manage species together in specific spots at priority areas for recovery of species. And so we started discussions about helping him out with this endeavor. And in fact, identifying spatially efficient priority conservation areas is really the bread and butter of what's called systematic conservation planning. And there are many kind of tools that allows people to do this kind of planning. There's SmartSand, there's Prioritizer. All of these try to address this, what's so-called a reserve design problem, which is, okay, how do we come up with a spatially efficient set of areas that help you achieve all your conservation goals across multiple species that have different distributions, different preferences, and so forth. So a few years ago, we said, okay, well, let's just try one of these out-of-box kind of tools, see if they work. We tried and we failed just because they were just too opaque. It just was not flexible enough to account for the huge complexities that managers have to consider when making these kind of decisions here in Hawaii. Because it's not only about the fact that we have hundreds of species that you have to consider, but it's access, it is helicopter time, it is all sorts of other factors that go beyond the biology of these species. So it's just something that none of these tools really allow them to do. And it's no wonder that when you actually go to the literature about this SCP type of tools, there's kind of a big implementation gap, which is a lot of studies out there of people trying these tools, coming up with really great plans. When you actually follow up and try to see actually what has been used in actual planning on the ground, there's a big, huge gap. And we wanted to do something as we were approached by a manager that really wanted to put this plan on the ground. We wanted to come up with something that would lead to better management on the ground concretely. So we ended up doing something completely different. We ended up coming up with our own way of prioritizing, doing spatial prioritization across this vast landscape across Maui. And we call this new novel approach TFE, SCP, meaning it's still a systematic conservation planning approach we have developed. But the TFE stands for the transparency of the process. F stands for flexibility, which allows for the inclusion of all those factors and criteria that managers have to consider in this type of decision making, all built into this process. And the expert engagement, just to make sure that this is a process that's driven by management needs and shaped from the beginning to end. So at the end, we know that we end up with products that really are going to be useful for landscape planning. So we do have, publication. We have an associated R package that kind of has the brains of this optimization algorithm we have designed. But as you see from this talk, we ended up finding out that systematic conservation planning is so much more than having a fancy algorithm. It's about thinking about the entire process from engaging with partners, going through the quantitative approach together, and also thinking about that bridge between analysis and actual planning. So indeed, if you think, when we first started this approach, we thought of things in a pretty simplistic way. We thought, well, what if we just subdivide the landscape into these like simple planning units, polygons, which are large enough to house individual populations of species. And you think about each species having in each of these polygons a differential suitability or a compatibility with these areas, and identifying areas across the landscape where the species are known to occur in terms of whether they are wild populations, wild occurrences, and so forth. Our algorithm started out just looking at that entire distribution of species across the landscape, their preferences, habitat preferences across the landscape. And this algorithm then would allow us to come up with what we call a conservation footprint that pretty much allows us to meet all of our conservation goals across all species in an efficient way, by picking areas that will allow you for the greatest co-management across multiple species, by picking areas that are as suitable as possible in terms of like habitat compatibility across all these species, and so on and so forth. But the thing is that just showing this slide here may give the impression that it was just a matter of stacking a bunch of species distribution models and seeing what comes out, kind of like a heat map approach. But the approach we did, again, really try to reflect the complexity of decision making that managers have to consider when thinking about where to work, which species to consider to work together in individual spots. So the approach we devised tries to indeed come up with that spatially efficient conservation footprint that allows you to meet your recovery goals across a vast number of species, but also it prevents, for instance, packing too many species together because you want to minimize, you want to some degree also spread out the risks. Also avoids co-locating compatible species because you may have risk of hybridization. You may have some species that are too hard to tell apart, for instance, for snails. So you may not want to manage them together because that will make it hard for you to identify. We also are able to set individual island or mountain-specific recovery targets for species. So when we think about, okay, for a particular species, for recovery, we would need to have 10 sustaining populations across Maui. You can identify how those targets were to be distributed across the different mountains or islands. And throughout this process, we also heard experts in terms of what they felt was necessary for that processing into reflect. So one of the things we heard very loud and clear is that, okay, it's great you have a habitat or a species distribution model for a species, but if you know a species likes a particular place and it occurs there, that is a priority area for you to pick for management because it's a lot lower risk for you to pick an area that you know the species occur than for you to try to experiment out plants species in places that we don't know if it's going to work or not. This ended up being then a process that was really about creating these very complex algorithms, but also throughout the entire process coming up with something that consistently required us to really engage with experts in all separate processes. And it started out from simple questions about, okay, what species to consider? Again, we were trying to do this for over 400 species, but there's got to be a threshold about what to include and what not to include. Again, for all of these species, what are the goals? How do you define recovery in terms of number of populations across the landscape? And how do you spread those recovery targets across all the different mountains across mountains? But then we know that everybody says this garbage in, garbage out. We had a lot of data for the species, especially for some of our taxonomic groups. That didn't mean that we didn't have to review each one of those data pieces with the experts to make sure that once we put them all into our fancy optimizer, we would be able to get good results out. So we came up with processes to essentially and tools to allow experts to review all of the data, revise them. So at the end, we knew we had good inputs going into this entire process. And again, all those decisions about, okay, under which situations are packing too many plants together, is that too much? Those end up always being very complicated. Well, it's based on which kind of species we're talking, whether it's plants or not, whether it's the same general or not. And all those discussions we have to have all those kind of discussions with the experts along the way so we can reflect all that complex rule sets into our algorithms themselves. So anyway, a lot of kind of decisions that we were checking back with our with experts and the planners and managers along the way to make sure that the process reflected those considerations. And the thing is that even after putting all these constraints in this process and coming up with this really complicated rule set to come up with these conservation footprints that would be necessary to reach the recovery goals across all these species, we found out that there's almost an infinite number of ways you meet that combined set of recovery goals across all species. And we found that, when we ran this algorithm, sometimes you would find a conservation footprint that would meet all of our recovery goals. Here, using an example for plants as a group, which was about 200 species. And some of those footprints were pretty compact. Some of them were a lot bigger. And so there was a lot of variability in the way that you could reach those recovery goals across all of your species. And they not only varied with respect to the total size of the area needed for you to reach recovery, but they also varied in terms of how much of those footprints were within native habitat or invaded habitat, how much of them were within or outside existing fences, within or outside existing biodiversity managed areas, in areas that were climate resilient versus not, in areas of high versus low high risk, accessibility, so on and so forth. So how could we pick a footprint, given that there's so many options and how they vary so much in all of these different type of really important criteria that managers care about? So to do that, we ended up, for all of the different species groups that we did this process for, we ended up creating a very large number of these conservation footprints. In the case for plants, which we had, again, 200 species, we're trying to find a map for recovery. We did this 1 million times. And then for us to pick the one solution out of that 1 million set of options, we ended up devising an expert-led tool, which we called a trade-off analysis tool, which allowed the experts that were part of this process to actually play around with those different criteria and see how, okay, if you really are trying to maximize or minimize the total area of a conservation footprint, what happens with your fire risk and so on and so forth. And I can actually try to see this will work. I think I have time, so I want to show kind of some of these tools online. I know it's a live demo and I know it's about to fail miserably as most live demos do, but we'll try. Let's see. Let me just give me a second quickly. Well, there is really a curse of translation right now.
Oh,
It's incredible.
yeah, let's test it ahead of time.
Yeah. Oh, here. Okay.
Share.
Okay. It just takes a little bit. Okay. I'm just gonna put it on the screen. So this is an example of this criteria trade-off tool. So what this shows here is all of these different levers that experts can play. And in this case here, we're telling, okay, all you care about is taking the footprint that minimizes as much as possible total area of a footprint. And what then it shows here is that if you do that, this is how your solution looks with respect to all of those different factors. In terms of like, okay, you're actually picking a solution that's pretty small, but it's doing, kind of like moderately okay in terms of like the percent of your footprint that's within ungulate managed areas and conservation areas and so on and so forth. So you can actually then start playing with these trade-offs and say, okay, well, what if you only care about picking areas that are low, let's say, that are as accessible as possible, or what happened with your trade-off? And what that shows, like, okay, now your accessibility is doing pretty well. You're picking at relatively accessible areas, but now your footprint actually grew a lot of size. So you can start, experts can start playing with all these different levers and say, okay, what's a combination of these criteria that's going to give you a good trade-off across all these things that experts care for? So we had for all these groups, we had all the experts and play with these kind of tools to identify, okay, what is a good balance of these factors that are important in decision making? And once they had decided what was a good balance for those, we could finally pick from that 1 million set of options that we had available for us. But that didn't mean that we're over, that this entire process was over. In fact, it was kind of halfway in between. So what happens is that we know that every time we would talk about any of these conservation footprints with a group of experts, people would like point to like one of those individual polygons and say, oh, but this area here is like, this is a landowner that sometimes grants us access, but it's really hard. Or like there's all these super specific local details that our spatial data would never be able to reflect. Even if we spend years trying to collect field data, those are the kind of like expert field knowledge that people have in their mind that never gets translated into input data. So we knew as we were doing this process, okay, whatever our algorithm spits out, it's not going to be perfect. And we're going to have to find a way to give the experts in this process control of completely modifying this process. And that's essentially what we ended up doing. We ended up devising a tool that once we had those conservation footprints that were, like, let's say, the best available footprint we could create based on our algorithms, we could then try to come up with, get the feedback from the experts to what we call fine-tune that answer to something that actually reflects everybody's understanding of on-the-ground realities. And I'll show you Okay, wow, it's working. Okay, good. So this is essentially, we ended up creating a full-on web-based, open access, but safe, like not anybody can log into this, collaborative GIS platform where then all the managers can go into this platform and review. Again, we're doing this for all plants, water birds, forest birds, land snails, terrestrial arthropods, and so forth. And for each one of these footprints, they can look at what the model spit out, and they can see, okay, for this particular planting unit, these are the species of plants that got picked for prioritizing recovery. But let's say, okay, well, actually, this species here for that particular unit is this not a good spot. That population is just one remaining individual. We should find something else. There's a tool that allows then the experts to go make those suggested edits. These edits then get discussed by the group of experts, and then they get accepted, and the footprint solution gets modified. And this obviously, you get to track all of these results. So these are some examples of some of the past edits that we have had in this process. Made, for instance, this is just an example. This is a species I got moved from one particular planting unit to another. Same here. You can see exactly who changed and why. In this case here for this Bigamia brachii, it got added to another plant unit that could be the species could be co-managed with other species. So anyway, we come up with then a process that all the experts, all the plant experts for across Maui can log into this and make this really reflect the reality on the ground for this plant. So we essentially we have been trying to do this for 7 different distinct taxonomic groups, again over 400 different species. All of these different groups we have had to do a slightly different process because we know all these groups are very different in their biology in terms of the available information we have. But we're pretty much done with 4 of them and nearly done with the 3 remaining ones. So it's super exciting. And it's super exciting because then at the end, I'm really testing my luck. This is the 3rd demo. But we end up having something like this. You can have a map such as this, which for essentially is the combined footprint for necessary for recovery across all different species considered in this effort. So you can see here, again, this is a group that I work most with. But in any of these areas you click, you can see exactly what are the seabirds that are slated for prioritizing recovery in this area. What are the plants that got picked, arthropods, snails, and so forth. So this is the first time that a manager has an idea what's the priority for recovery for all these different species at the entire landscape scale. And this is something that just was not possible before. And I don't think any expert, I know we have incredible biologists, a lot of people that have spent decades in the field working with plants or snails, but I don't think anybody has been ever able to synthesize this kind of information collectively into a single kind of plan. But then we went a little bit further because as we're making these revisions to this footprint, we started thinking about, you know what, this is all going to change. As soon as we're done with all this fine-tuning experts, change our map to reflect the best available information they have now, then we're going to have threats. We have climate change. New species get discovered. We have new population discovered. We have new techniques for conservation that allow other places to now become available for management. And I didn't want to spend all this time developing this product to then the day after it being obsolete. So now what we're doing is we're working as part of this end of this project that a tool that I showed you for fine tuning or editing that footprint is now going to be essentially a platform that's going to treat all these plants as a living product. So every year you have let's say the plant team goes out and discovers a new species, or they find out that one of the populations have been trying to manage for recovery is not doing well, responding well to management. They can actually go to to a platform like that and make those edits. So this plan actually gets edited to perpetuity, and we don't have to redo this every 5 years or every 10 years and spend a lot of money. So I'll switch a little bit from then this process to actually the benefits we have seen so far from this. Because it's been really notable. Again, we're not fully done with this. We're like 95% done with the actual analysis. We have a lot of writing to do, but it's another issue. But because we have been seeing really concrete uses of this, which is really heartening, because again, that was the whole purpose why we ended up doing something completely different from what was previously done, because we wanted to make sure that at the end it had on the ground consequences. And again, just having that broad landscape level plan of like identifying priority area for recovery across all these species, not only plants, but all these taxon groups together, is something that was just not possible before. So people like Scott Fretz that are trying to coordinate, all these different species teams across the landscape, knowing where those opportunities for co-management, where those priority areas that they need to like really hammer on, and having concrete asks of what are the places that they can feel that have the greatest impact on overall recovery across species is something that it's just been extremely valuable. I'll show you additional examples later. If you're not thinking about that 30,000-foot island level or multi-island level planning, this still is a kind of tool that has been shown to be really useful also for reserve level planning if you're like managing individual parcel, or even if you're just managing individual species. I'll show you some. So in terms of that landscape level planning benefits of this process, these are all kind of examples that DOFA has provided that I'm sharing with you today. So, this is an example of Maui where the areas in green are areas that are currently being managed with at least a partial mandate for biodiversity conservation. Areas in red are areas that are currently being fenced or in the process of being fenced. And, state and partners are always looking, okay, where else to expand this fencing network? So, what are the priority areas that we should manage or that we should expand our fencing? And, now they have a really clear tool, because once you start overlaying our results with those maps, they can start seeing, okay, what are some of the places where you can actually add a lot of other species in that recovery portfolio by expanding that fencing network across the islands. And it's not only about fencing, but it's like the same set of data has allowed the state to identify additional projects that they need to be discussing, because it has happened that we have pointed some areas that are currently either owned or managed by partners that they haven't engaged as much recently. So those are the points, okay, these are the people that we have to start talking to make sure they're on board with this plan. And in some cases has led to them considering additional acquisitions of land for places that they feel that's strategic for them to have control to manage for recovery across these islands. And if you're managing individual land parcels, this also has been really useful. So again, state has recently been considering the expansion of the Pu'ali'i NARS in Molokai. And this was at this particular valley at just east of Kalaupapa Peninsula, Waikolu Valley. And they were considering about whether or not this should be added, protection added to the Pu'ali'i NARS. And with the tools that we have developed, they were able to see exactly what were the assets that would be valuable in terms of conservation, and what would be the things that makes this an area as an additional contribution to the particular NARS. And they could see exactly the kind of species that would be targets for recovery in that area. And this is the kind of information that normally would take a lot of meetings with the staff, all of the different teams, even within DOFA, talking to each one of them and understanding exactly what each one of those teams know about this particular area and so forth. And now it's all consolidated into a single system. Lastly, as I mentioned earlier, we did this essentially, these were 7 parallel processes because we had to apply this process in 7 slightly different ways across these 7 taxon groups. And it's really, I'd just like to highlight the example of the land snails, because that is one that I felt like had probably one of the most concrete impacts so far. Because as you all know, land snails here in Hawaii, Oahu, Maui, and so forth are really seeing some really consistent warning declines. And Maui Nui, unfortunately, was kind of lagging behind the number of kipuka kahuli or snail enclosures across the landscape. And right now, it's really critical that we have these snail enclosures across the landscape as safe habitats for these species to persist and be protected from all sorts of threats in terms of the indigenous snails, invasive ants, and so forth. And they really wanted to have a better idea of, okay, if we have, all these over 60 species that are concerned about their long-term persistence across their landscape, what is the minimum number of enclosures they would need across the landscape to make sure they have representation of the snails at least 3 replicates of population for these snails across the landscape. And we use the same process to identify essentially a kipuka kahuli network that is the smallest number of enclosure or kipuka kahuli necessary for you to achieve that goal of preventing extinction of these snails. And in fact, Scott Fretz is already allocating funds to start construction of some of these sites as soon as this comes this summer. So super exciting. And this goes to the broader benefit we hadn't expected when we started this process, is that once you go through these processes that are so deliberate and systematic about identifying recovery needs across the landscape, it's so much easier for managers to identify what are their asks for conservation. And again, we are not done with the project yet, but DOFA has, based on some of these preliminary findings and so forth, they have already secured over $4 million in funding for on-the-ground conservation across the different islands, based on some of the for some of these results. So, kind of thinking a little bit more broadly about what we have been going through over these last few years is, again, we started out thinking that we're going to be building some fancy algorithm that was going to solve our problems. And that's definitely never the case, because we have now realized that it's systematic conservation planning is really about the whole process, from getting people on the table, co-producing something together, and seeing the entire process through down to the implementation phase. You can't just create a map and walk away. That's not going to work. And the other aspect of this process that has been noteworthy is that true aspect of co-production. I think we all like to use that word around, but this was intense. Like, we have been meeting with our management partners in this process weekly for the last, 3 or 4 years. And it's like, I must be frank, there's times where they have, given it's really a co-equal process, they have taken the process and pushed it on, like, oh my God, this is going to take so much work. But it's like what they want. We went for it. And so anyway, it has been a really intense process of co-production. And at the end, I think we kind of have come up with something that I'm not sure it needs a name, but I think the way I like to describe it succinctly, it's called algorithmically supported co-production, which is all these processes. If we're like trying to get people to like find a common time for us to meet and all travel to the Doha base yard, Maui, and make those decisions together, it would have taken such a long time. And instead, we kind of like been developing all these custom tools that some of like the ones that I showed you that allowed people to pitch in, collaborate, and make those decisions in a way that was a lot more frictionless. And I mean, I just showed a few examples. I literally have a running list of like 3 pages of custom tools we have developed in this process to allow us to do this. But so I didn't think that app development was going to be part of my research ecology portfolio, but it's kind of been super easy. But so then what happens is that, I've been a quantitative ecologist for a long time. And I have always known that algorithms alone would not allow us to get to where we got to in this process. But I also have to realize that, again, as I mentioned earlier, experts alone would not be able to do this as well. Because again, there's not a single person that has all this information together in their brain. And even if they had, they would not be able to put it down on a map. So this is really a process that allowed us to leverage this power of both the collaboration and the technology to come up with something that neither of those aspects would be possible, would be able to do it alone. And then lastly, to wrap up, is we also have to be humble about this whole enterprise. The Maui Nui landscape conservation planning effort is something that's been led by Scott Fretz with that huge overarching goal of like identifying how to do better conservation more efficient across the landscape. And the where part of this question is what we have been trying to address, but obviously that's only one question. It's what actions, the costs and the benefits and all those things. And there's been all these other really important efforts that have been going parallel that try to answer some of these questions. And Melissa Price has been leading a really important part of that aspect, a component of that work. So we have to realize that, yeah, even though this looks really cool, there's still other important questions that we have to address and also integrate. So we really come up with a very comprehensive, systematic approach of conservation across the landscape. So again, we're almost done with this entire effort for Maui Nui. We're now thinking about what's next. We'd love to do this in other islands, other Pacific islands, mainland. We're looking for support and partners. But in the meantime, I'd like to, again, give us huge thanks to everybody involved, my spatial prioritization team, all the people involved in this process, the experts, the managers, the planners, and very importantly, all the funders that made this process possible, because it has taken a while because we've been building these tools, as we were going through the process. Now we're slated to do this a lot faster because all of our tools are ready to be deployed elsewhere. But again, PICAST, US Fish and Wildlife Service, DOFA, USGS all have pitched in with a significant funding to make this process possible. So with that, any questions?